Swayam Prabha. Digital India. Educated India.
Very good morning to everyone, those who are present here in person and of course those who are joining us remotely. So welcome to the day 4 for the GYAN course on characterization of heterogeneous catalysts, bulk, surface, in situ and operando method. In the last few lectures that I delivered, we were talking about how the catalyst is really dynamic during the reaction condition, and how we or why we should need to know about the dynamics of the catalyst, and then that will just give us information about the state of the catalyst at the surface, and then its behavior, the nature of the active sites and all, and how that is affecting the overall reactions and all. So, today we are going to start with the X-ray based techniques. So, we will cover the principles a little bit and then its application in catalysis with few examples that we are going to see. So, before that, this is something that Professor Banares has also uh, uh, talked about in his lecture, is that the interaction of light with matter, and that is where the spectroscopy comes from. So, when we have a electromagnetic radiation, the matter or the substance which are under investigation, they behave to this electromagnetic radiation differently. So, on the bottom we have the wave number that is increasing, or in a simpler word, on the top we have the wavelength increasing. So, the smallest wavelength are the X-rays, and as we go through the UV, the visible, the IR and so on. So, today's focus is how these X-rays they interact with the matter, and from that what different kind of information we can extract. So, we are going to specifically cover three topics: the X-ray diffraction, which is probably very popular among the solid catalysts, X-ray photoelectron spectroscopy, another one X-ray absorption spectroscopy, which is not widely used because we need synchrotron X-ray sources, which is not easily available. So, we will start with the XRD. So, let us just start with little bit of the history. So, in 1855 the X-ray was first discovered by Conrad Roentgen, and then in 1912 Max von he proposed that the crystalline materials they can scatter X-rays, and for that he got the Nobel Prize in Physics in 1914. Now, these X-rays are of very small wavelength, what we saw with that electromagnetic diagram, and they are of the order of 0.5 to 2.5 angstrom. Now, which is actually comparable to the distance between the atomic planes of which the molecule is constituted of. Because it is of the same order, we are able to get information about the lattice distance and all these things, and from that we are able to identify which crystals is under investigation. So, it is a very widely used experimental technique. So, it is not just in the field of catalysis or material science. I mean, it goes back to the polymer science, metallurgy, structural biology, even pharmaceutical science, and of course, ceramics, glass, geology and mineralogy. And what we are going to focus is on catalysis, especially identifying the type of the material and their crystalline phases and how those phases evolved during the reactions and all. So, before we go, I mean, this is just a hint that the XRD is used for so many fields. Just a quick question, like what do you think, how many Nobel Prizes have been given uh, till today related to XRD? Okay. Any answers from online participants? Any guess? I have already given you one Nobel Prize here, so it cannot be 0, it has to be 1 or higher than 1. Any guess? 5, 10, 12, 3? Okay, 25. Okay, it's about exactly 25. So, there are 3 physicists who developed techniques in XRD, and then the 22 scientists for applications of XRD in different fields. So, this is a small list, well actually this is the full list of those scientists who got the Nobel Prizes, and when we share the course materials you can just go over it and then just read about for what contribution they got the Nobel Prize and all. Okay, so moving forward, how does the XRD work? So, we have a beam of X-rays that interact with the matter, and the matter elastically scatter those X-rays. Now, those scattered X-rays, they interact with each other, and that interaction can be constructive or destructive. When the interaction is constructive, we get huge signals. When they are destructive, it is a very low signal. Okay? And that depending on the angle of the X-rays at which the sample is irradiated and the constructive interferences that we are seeing, we can actually back calculate or get information about the matter. So, how does it done? So, this was done by the Bragg's law, which was proposed by William Henry Bragg and his son William Lawrence Bragg. Okay. And it was proposed in 1930, and for that they got the Nobel Prize in 1915. So, how it does is that let us just take this is our crystals where we have the atomic planes, and these atomic planes have distance between them as d HKL or simply the d. Now, we have the incident X-ray which is coming at an angle theta to the atomic plane, and then it is scattered from the plane at another angle at the same angle which is theta. So, there is actually a difference between there is the angle that is 2 theta between the incident and the scattered X-rays. Now, if we look at the atomic distance, so if this angle is theta, then this angle is going to be theta, and since this distance is d, from the simple trigonometry we have this distance is nothing but d sin theta. Okay. And for a constructive interference, what we want is an integer difference between the wavelength of the incoming scatters. Okay. So, this is the half distance, that is the difference between this plane, and this is the other half. So, this needs to be half of the wavelength, and if the wavelength is lambda, the half of the wavelength is lambda by 2. So, what we have is that lambda by 2 is nothing but d sin theta, and from that we have the equation lambda is nothing but 2d sin theta. Now, that is for the first plane. For the second plane, it does not have to be lambda by 2, it can be 2 lambda by 2, which is nothing but lambda, that is the full wavelength, and we will have another constructive interference, and hence the equation comes, that is n lambda equal to 2d sin theta. And this is the Bragg's law, which defines at what theta we will have the, or to be specific, at what 2 theta we will have this constructive interference, and based on that, since the atomic arrangement the arrangement of the atoms in different crystals are going to be different, and hence the theta is going to be different for the constructive interference. From that we will get to know what type of the material that we are investigating. Okay. So, this is a simple schematic of how XRD works. So, we have of course an X-ray tube, and we have a bunch of primary optics through which the X-rays are focused on the sample, and then on the other side we have the secondary optics through which the X-ray goes to the detector. Now, what happens is that your sample is stationary, this is just an example, and your beam of X-rays that is incoming, that is going at an angle theta, and your detector is moving at angle theta, so that the distance difference between them is always 2 theta, which is continuously followed. And these are some of the ways where how the typical commercial XRDs work. So, we have the sample in stationary state, the X-ray tube and the detector moves both towards each other at speed of 2 theta, or we can have the X-ray tube moving at theta, the sample is also moving at theta, such that we have to move the detector at a speed of 2 theta, such that the Bragg's law is always followed. There are other ways, instead of reflecting from the sample, we can just pass it through the samples, and the 2D detector just moves at a speed of 2 theta. And I just want to mention that these X-ray beams are not focused on the samples, but rather they are treated as parallel beams. Okay. So, since we are going to talk about in situ techniques, where we look at the material in certain gas environment as well as a different temperature than what we saw in the ambient conditions. So, this is one example where we have an environmental cell or an in situ cell where we can collect XRD data in some controlled environment and a different temperature. So, few specific things on these things are that we have the graphite dome, which is pretty much transparent to the X-rays, and X-rays can just pass through the graphite dome. We have the sample seated here at the center of the cell, and then we can raise the temperature because we have the heater element that is present beneath it, and then we have options for gas inlet as well as the cooling, because there are O-rings which separates the outer environment to the inside environment, and this is the same cell connected to the XRT equipment. Okay, little bit about the X-ray source and all, and how they are going to affect our data collection or the quality of the data that we are looking at. So, how X-rays are typically produced is that we have high voltage that produces heat, and because of that electrons are emitted, and these electrons are accelerated at a very high speed towards another material which is called the anode material, and because of this beam of electrons are bombarding on these anode material, we have the X-rays that is generated. So, if we look at by the atomic arrangement, when the X-rays are generated, these photoelectrons are emitted, and we have electrons at the higher cell which is going to fill for the hole that is created at the core cell, and if it is coming from the next electronic cell, it is called a K alpha line, because these electronic cells are at a lower energy than this thing, and then when they come they emit energy, and this is even at a higher energy, and when they come they are going to emit even more energy, and these are the X-rays that is being radiated from the sample, and then if it comes from the next neighbor, it's called the K alpha line, it's next to next one, it's called the K beta line. According to the energetics that we just discussed, the K alpha line is stronger but lower in energy, but the K beta line is higher in energy, but it's not as strong as the K alpha line. Now, this K alpha line is the typical ones which are used in the XRD, where the K beta lines are nothing but the fluorescence that causes some background informations. Now, we talked about the electron being dissipated from a heated element. So, this is called the cathode. Now, typical cathode material in the XRD tube are of tungsten filaments, whereas the anode material can be different, because the anode materials are the one that generate the X-rays. So, depending on the material, the energy of the X-ray which is related to the wavelength of the X-ray is going to be different. So, the typical benchtop XRDs that we have in our academic institution or scientific labs is has the copper as the anode source. This is very popular, that is most common, and as you can see, the wavelength of the X-rays coming from this source is roughly 1.54 angstrom. Whereas, if we have samples where the atomic distances are even smaller than this, the 1.5 angstrom, in some of those cases molybdenum can be used as a anode material. And there are also few uses of cobalt which gives low fluorescence, which comes from this K beta line. Okay. So, depending on the anode or the X-ray source, the penetration depth and the peak intensity are going to vary for the X-ray diffractogram that you are going to see. Okay. Okay. Then we will talk just briefly about the sources of the X-ray. So, on in our lab, it is just the X-ray tubes. Lab means the benchtop XRDs that we have in most of the academic institution or scientific institutions. The X-ray tubes are the one which generate the X-rays, but those the energy associated those X-rays are not significant as compared to the ones that we see in a beam line. and a synchrotron beamline. So there is up to 10 to 20 orders of magnitude difference in the intensity, and hence what the synchrotron X-ray sources can do on the typical benchtop X-rays cannot do. But I mean, at least we have X-rays at our disposal at hand without too much of waiting, which can still give us information for which we have to wait for a long time for the beamline experiments. Okay, so with that little bit background on the XRD principles and on X-ray sources and all, let's just look at a few applications. So before we go into those applications, so here is one typical X-ray diffractogram. That's how it looks like. And then there are few things that we can get out of it. So something is like the position of the peak, it can be the intensity of the peak, there can be the area under the peak, and in one case if we have fitted that peak, we can actually calculate the full width at half maximum. So it is nothing but the width of the peak at half of the maximum height of that peak. Okay, and all these informations are going to be important in extracting different parameters. Let's just look at some of those things, how XRD can be used in different ways to get information which is relevant to the crystalline structure of the material. So the most common use of XRD is to determine the crystal nature. Okay, and here is an example where we have the X-ray diffractograms presented as the intensity of the peak versus the 2 theta, and what I am showing here is an magnetite phase which is Fe3O4, which has been oxidized at different temperatures, and what we are going to follow is that different oxidation temperature, how is it converting the magnetite phase to the other oxide phase of the iron. So at 25 degrees Celsius, what we see is that still the magnetite phase is present. The same is the case with 250 degrees C. These are the two principal peak for the magnetite phase. But as we are calcining at a higher temperature, which is 350 degrees Celsius, what we are seeing is that now we have different peaks which are corresponding to the gamma phase of hematite. And as we are going to even higher temperature, that is 600 degrees Celsius, our peak sharpens, and now we are seeing the alpha phase of hematite. Now how these things are done? So typically what is done is that for years and years, we have several reference materials. For example, we have the magnetite, we have the gamma or the alpha phase of the hematite, and the XRD pattern of those reference materials have been collected and stored in the database. So previously there used to be a huge book which collects all the X-ray diffractogram of these reference materials, but these days all these things are available online, and typically these are provided with the software for the instrument that we are using for the XRD data collection. And just matching with those database, we will get information about the type of the material or the nature of the crystalline material that is present in our sample. Okay. So moving forward, let's see what else we can do from the XRD. So on the previous slide, we saw one type of phase, that is either a magnetite or a hematite, and among the hematite it is alpha phase or the gamma phase. But now we see can we detect a solid solution. So this is something Professor Banares was also talking yesterday when vanadium was going inside the titania phase to make a solid solution. These solid solutions are nothing but a mixture of couple of oxide phases. Okay, and how XRD will be able to detect these things. So this is an application for high temperature water gas shift reaction. So a little bit of background. So the high temperature water gas shift reaction has copper, chromium and iron oxide present in it, and the problem is that this iron oxide in its hexavalent form, it's carcinogen, and hence we need to replace iron, replace the chromium. And some more background is that what is the role of the chromium. What people have found is that the chromium makes a solid solution with the hematite phase, and hence it stabilizes the bulk phase of Fe2O3, which helps in higher activity. So one condition for finding a replacement of chromium is that we need to find a material which can make a solid solution with iron oxide, just like the chromium was doing, such that we can have that stable phase, and hence it can be a potential substituent of chromium in the industrial catalyst. For that, here the authors they tried 3 different earth abundant material. One is silicon, the other 2 are being magnesium and aluminum. And let us just look at the XRD patterns of these materials. So, on the left hand side we have the chromium iron, which is of course the base material for us, because that is the industrial catalyst, and then substituting chromium we have aluminum iron, magnesium iron and silicon iron. Then on the plot B we have copper as a promoter added to it. I mean, looking at these diagrams, it seems all of them have almost the same XRD pattern, but if we zoom in to the most significant phase of Fe2O3, which is present here around 35 2 theta degree, what we can see is that iron oxide has a peak at 35.85 2 theta degree. Chromium is not so different in ionic radius than iron because of the similar atomic mass. So, addition of chromium only shifts it a little bit, only by 0.06 degree. Whereas, we have to keep in mind is that aluminum, magnesium and silicons ionic radii are far different than the iron. So, if these materials are going to make a solid solution, then we are going to see a significant shift on the iron oxide peak, because these elements are going to be in the lattice of iron oxide, and hence your lattice structure and the bond length and all are going to change, which is going to be reflected in the 2 theta degree. Okay. So, we see for the aluminum it is a significant shift, and so, same for the magnesium it is a significant shift, but silicon being significantly different ionic radius than the iron, there is only a very little shift, which is 0.05 degree, and from that the authors concluded that the aluminum and the magnesium, they form solid solution with iron oxide, whereas silicon does not. There are other criteria if they are the better substituent of chromium, but we are not looking into those things, but at least from the XRD we are coming to a conclusion that the aluminum and magnesium can be a potential chromium substituent, where silicon, since it cannot form a solid solution with iron oxide, there is a less probability that it will be able to stabilize the Fe2O3 phase, and hence the probability of silicon being a potential chromium substituent is less. Now, let us look at another application. Now, what we can do with XRD is determination of the crystal size, but before we go into that, so I will just give you a little bit of information on the plots that I am showing here, and then I have few questions to ask. So, background information is that these are the XRD patterns for cobalt platinum 3 nanoparticles, and high resolution TEM images have been collected on these samples. There are 2 different samples, sample A and sample B, which are prepared in 2 different ways or were allowed to grow for a different duration, such that the sample A mean diameter is 5.1 nanometer, whereas for the sample B it is 8.4 nanometer. So, this is from the TM images, and now we are looking at the XRD of these 2 samples, and we are trying to figure out can we determine the crystalline size from here. Okay, so, before I move ahead, just a quick question. So, now that you know you have 2 different samples of 2 different sizes and they have the XRD patterns here, what are the differences that you are seeing between this and this? Yeah, online participants can just type their answer in the chat, and we have our moderator here, Mr. Rajan. Yes, there is difference in the intensity, that is true. In one case we are about at 4000 counts, in other case it is close to 6000 for the bigger particles.
So, there is an answer from the online.
Yes, please.
Particle diameter and intensity.
Particle diameter, I mean we have not gone into the particle diameter yet, but that we will look next. Yes, intensity is something that we are seeing.
And one more answer from Suraj, FW had some difference.
Full width at half maximum, okay. that is also correct, but I will just elaborate that a little bit. So, the full width half maximum is because the sharpness of the peak are different. Okay. So, two things we are seeing, of course, the larger size crystals we have higher intensity, that is number one, if there is no other crystal defects that we are going to see in the next slide. The number two is that the peak becomes sharper and sharper. So, this is
Crystallinity varies.
huh?
One more answer from
Yes.
crystallinity varies.
Crystallinity varies, we are not sure about that at present, because from the, well, we will look into it, it is just the size at present. Okay. Okay. So, what we are seeing is that if there is uniformity in the crystallinity, which was gone little bit from the other experiments, is that we have, for the bigger particle we have higher intensity, as well as the peaks become sharper and sharper, which someone just said who is participating from the online, is that the full width at half maximum is going to change. Now, there is something called a Scherer equation, the formula is given here, and with the typical parameter values here, or what are the different things, and what we can do is that the this 111, 200 and 220, or maybe just 311. So, what we can do, just we can fit these individual peaks with our typical softwares, and then from that we can get the full width at half maximum. So, that full width at half maximum is nothing but the beta in this equation, which is given in the radians, right. And using that equation, so k is nothing but a dimensionless constant, and typically the parameter is about 1, and lambda is the wavelength of the incident X-ray, and that depends on the type of the X-ray source that is being used for that equipment. Typically, it is a copper K alpha radiation, and it would be about 1.54 angstrom. Okay. So, from that we can actually calculate the particle diameter. Now, you see whether we are taking the peak at 111, 200 or 220, in all cases the diameter of the particle that we are getting is pretty close to each other, say 5.09 versus 5.33, 4.98, they are pretty close to each other. Same is the case where we have the diameters like 8.4, 8.5, 8.2, all these things, and that is also pretty consistent with the TEM mean particle diameter that we received. Okay. So, this is one applications where we can use the Scherer equation with different peaks such that we can back calculate, well, we can calculate the average particle diameter for the crystalline material that we have. But then there is one thing that we have to be really careful about, and that is if well, I mean, okay, so this Scherer equation has two factors, its applicability. One is the primary factor, which is nothing but the particle size. So, if particle size is different, but they are uniform within the same sample, then this equation is applicable, but there can be some secondary factors. Now, these secondary factors that we have to keep in mind. For example, there can be inhomogeneous strain or stress in the lattice. This strain or stress can be just because of the way the sample was prepared, or maybe because the sample was exposed to a different environment, which is the case in our catalytic reactions. So, what will happen is that if the strain is uniform, it will either shift the peak position to a lower 2 theta or a higher 2 theta. But if this strain is non-uniform, then we will have the broadening of the peak. Okay. And there could be other factors such as lattice imperfection, stacking fault. Stacking fault is nothing but how these layers are stacked over each other, if they are perfectly following the atomic arrangement, or there is little bit of imperfection in that. And of course, there could be chemical inhomogeneity, which is like you have some trace amount of foreign material that is incorporated in the sample, and that is what we saw for the solid solutions, and a little bit of some other oxide phases or the impurities, they can change your atomic arrangement and all. So, what happens is that and then you need to have the particles of uniform size, uniform in the sense like they should be isotropic in nature, such that their properties are not going to vary based on their direction. But if the particle size in one dimension is significantly different than the other side dimension, for example, instead of a spherical particle, if we have rod like structures, then the particle properties are going to be anisotropic. So, in one direction the property is different than the other direction. In such cases your Scherer equation is not going to be valid. And how do we know that? That is why we are doing the calculation over multiple peaks. If we are going to see the similar outcome, similar d value from all the peaks, then we have a fair idea that the particles are of uniform in nature, like a spherical particle or something like that. But if it is a rod like particle, we are going to have different values, like significantly different values when we are looking at the XRD peaks and all. Okay. Yeah.
Yes, there is a question from Akash. I think he is trying to ask the K value is always 1. Why?
Well, I do not have an answer for that. It is a empirical parameter. So, that has been connected with different things. For example, we calculate the particle size from other techniques, and what K value gives us the best estimate of that value. From there we estimate. It is an empirical parameter, there is no mathematical equation for it. Okay. Yeah. Okay. So, if this part is clear to all of you, let us just go ahead and see in what other ways XRD can be applied. So, the one thing is composition determination. Okay. So, we looked at if there is a single phase, definitely XRD can help us. We looked at if there is a solid solution, XRD will be able to tell us if there is a solid solution or not. We looked at how we can use Scherer equation to calculate the particle size from the XRD, and then let us just look at how XRD can be used to find the composition. So, again this is going back to the original thing that I was saying about the XRD database. So, the reference materials of different crystalline structures, different oxide phases and all have been collected and put inside a database, right. And then what we do is that if we have a material here, in this case it is a nitride iron tool which has composition of oxygen, nitrogen, iron and chromium. So, we need to have that information a priori, that what are the elements present in my material. Okay. Once we have that information, then we can have the X-ray diffractogram and then connect it is done automatically through the software. We can tell, okay, these are the materials that is present in my sample, and based on that, what do you think, like what are some of the phases that could be present in my material. Okay. And that is given by the software, and then this is the qualitative nature. We can actually go quantitative, where what we can do is that if we have a priori information, for example, here when we know that, okay, these are some of the phases that is present in my material. Now, if I have information that what could be the structure or the model for those materials, and we use those as input for the analysis, this is like a nonlinear least square method, such that the error is minimized, which is shown here. We can actually back calculate the composition of each of these oxide phases that is present inside the material. Okay. Yeah, there is question. Yeah.
It is just a following question. He is trying to ask again, is there any physical significance of K, or it is just a constant?
I do not have a good answer for that. I will get back to that. Okay. Yeah. Okay. So, we looked at the composition determination. So, qualitatively it can be done, because if you know what are the material that is present in your sample, you have the database, and automatic fitting can be done to figure out what are the possible oxide structures that you have present in your material. But then again, once you know those possible oxide structures, and if you have some prior information about the structure of those oxide phases that is present in your material, you can do a nonlinear least square analysis to have actually the percentage of these things present. But there are few things to be taken care of. First of all, you need to know the structure very perfectly, that is number one, and number two, there should not be any imperfection of this material for the real material. Otherwise, there will be a difference in the structure that you are giving as an input and what the system is collecting as an experimental data. And then some of the things that has to be taken care is that the data collection should be really slow, such that for one peak we need more than enough points to fit those things, because here it is a least square method, and more the number of data, well, not exactly in general, but typically we need a minimum number of data sets for the best fit. Okay. Few experimental considerations, because most of you would be using XRD as one of the major technique for your sample characterization. So, one is beam focusing. So, these are the two cases that are shown. In one case, the beam is focused completely on the sample. In other case, the part of the beam is actually on the sample containing material. And then when we see the XRDs, for the case where we have a very perfect focus, we get a very nice X-ray diffractogram. But for the other case, now you can see there are two additional peaks which are being shown in the XRD, but that does not correspond to the material. So, this anomalous peak will be created, which will actually be really unhelpful, because now we are seeing things which are not exactly present in your material. Another thing is the particle size or the grain size. So, these are two examples where we have really small grains, well, I mean between 100-150 microns, whereas in the other case we have much higher, some 300 to 500 microns, and as you can see, the surface is not as smooth, and hence when we are collecting the XRD, if you see for the fine particles, we have very nice and clear peaks. But for the others, the intensity is really small. The case B here is almost half of the intensity than this case. Okay. Okay. So, is there any question? If not, then we will go into two case studies for XRDs. Well, not exactly case studies, but couple of applications in catalysis field. No, right? Anyone from here? No? Okay, cool. Okay, so the first one is on oxidative coupling of methane. I mean, in Europe, Russia, as well as in US, there is abundance of natural gas, and methane is the major component of that natural gas. And what we are going to see is that how we can convert the methane on site to a value added product, and this is one such experiment or one such pathway where the methane is oxidatively coupled to form ethylene, right. And at present, the sodium tungstate deposited on amorphous silica and manganese added as a promoter is the best catalyst in the literature. It has the highest yield for the C2 products, about 30 to 32%, and has a long term stability in the lab scale, at least tested for about 1000 of hours. Okay. But still, the role of manganese and the oxide phase of sodium during the reaction was not clear until a very late time, and this is a work published couple of years back in Journal of Catalysis, where Professor Banares was also an author and contributor. So, there are actually more beautiful data on the Raman for this catalyst, but since we are just going for the XRD, I am showing these things. In a later lecture, if there is a connection, I will show those Raman data as well, and how we can extract the two things like the structure of sodium tungsten as well as the role of manganese, which is the promoter for this catalyst. Okay. Okay, so what we are seeing is that the catalyst on the left side is just sodium tungstate on silica, whereas the catalyst on the right side, it has manganese as a promoter added to the sodium tungstate on silica, correct. And we are oxidizing the catalyst. It's like a temperature program oxidation kind of thing, and we are starting at lower temperature like 50 degrees Celsius and going up to very high temperature 800 degrees Celsius, because the reaction typically happens between 750 to 850 degrees Celsius. So, this higher temperature is actually corresponding to the reaction temperature, correct. So, what we are seeing is that first of all, let us just look at the things one by one. So, the alpha cristobalite phase, beta cristobalite phase are nothing but two different crystalline phase of SiO2. So, when the material was prepared, it was amorphous SiO2, but when the catalyst was calcined at higher temperature during the preparation, because of the presence of the sodium, the amorphous SiO2 phase gets converted to the crystalline phase, and this crystalline phase typically at room temperature is seen as alpha cristobalite, which we are seeing here for about 200 50 to 300 degrees Celsius, the alpha cristobalite phase of the sample is present. Whereas, if we go to higher temperature starting from here 250 to say 800 degrees Celsius, as you can see, there was this peak at about 2 theta of 36 degree, which corresponds to the alpha cristobalite, but then there is this other peak which is about 35.5 that corresponds to the beta cristobalite. As we can see how the phase transformation from the alpha phase to the beta phase is happening around 250 degrees C, and that is what we are able to see from the XRD. Before this type of in situ experiments, people were suggesting it is the alpha cristobalite phase which is the equilibrium phase of the support during the reaction. But now what we are seeing is that alpha cristobalite phase is totally not present during the reaction, it is the beta cristobalite phase that is present. Okay. And from other experiments which I am not showing here, this is actually a reversible phase transition. So, you come back from higher temperature to lower temperature, the beta to alpha cristobalite phase transformation will happen. Okay. Now, let us look at what is happening to the sodium tungstate, because that is the active material that is present on the support. So, we have sodium tungstate which is present say in this case. So, okay, this is pretty clear. So, I will just follow this peak, others are correspondingly the same. So, from room temperature to about 550 or 600 degrees Celsius, we have the cubic phase of sodium tungstate present. Okay, good. Then we go higher temperature which is about 600 to 700 degrees Celsius. Now, the sodium tungstate phase from the cubic to the orthorhombic, that phase transitions happen. Okay. But beyond that 700 degrees Celsius, we do not see any peak, it completely disappears. So, where did that sodium tungstate go? Because 700 degrees Celsius is not the reaction temperature. My reaction temperature is 750 to 850 degrees Celsius, and I am not seeing sodium tungstate from XRD. Well, I mean, we need a little bit of background information. So, the melting point of this crystal is 690 degrees Celsius, which is 700 degrees Celsius. So, beyond 700 degrees Celsius, this crystal melts. So, that long range order is gone, XRD cannot see it. So, what has been proposed previously is that sodium tungstate is the active phase, the crystalline phase of sodium tungstate that is doing the reaction, but it is actually not present during the reaction. Now, it is present in its molten state. Now, phase transformation is one part that can cause a difference in your activity. The crystalline phase getting melted to another phase, which is probably an amorphous phase, is going to be the another part. Okay. Now, let us see how things are changing when we are adding manganese. I mean, I am not following the manganese oxide phases, I am just trying to show you how the addition of the manganese has an effect on the melting of sodium tungstate. Okay. Same peak we will follow here. Here the cubic phase was present up to 600 degrees Celsius, then the orthorhombic phase present, but here now at 500 degrees Celsius my cubic to orthorhombic phase transition is happening, and as you can compare from here and here, the band intensity has significantly gone down, it has become broadened, right. That means the crystallinity of the sodium tungstate has gone down, what we just saw a few slides back, correct. But now what is more interesting is that at 700 degrees Celsius, the melting was happening. Okay. Now, that melting is happening at a much lower temperature, which is 650 degrees Celsius. Okay. So, one conclusion we can get is that this manganese oxide is somehow suppressing the crystallinity of the sodium tungstate as well as favoring the melting of sodium tungstate, correct. I mean, we are not getting exactly how these things are helping in the catalytic reaction, but at least this is the structural information we are getting from the in situ XRD experiment. Okay. There are a bunch of different experiments which are conducted, I am not going through the full story yet, and that shows how manganese acts as a promoter in this catalyst. Okay. Okay. So, if that is clear, then let us just look at another case study, and this is on chemical looping oxidative dehydrogenation. So, oxidative dehydrogenation is something that we have been talking, well, I mean Professor Benares is talking in the last couple of lectures. This is a chemical looping method. So, instead of sending both the hydrocarbon and the oxygen at the same time, we are actually separating it. So, half cycle, the hydrocarbon will come, another half cycle the oxygen will come. Okay. So, this is like a looping reactor. So, and I have an oxide catalyst which is able to donate oxygen in a redox manner such that the reaction goes on. Okay. So, for this oxidative dehydrogenation, we have ethyl benzene that is getting converted to styrene. Okay. So, on one side we have the oxide catalyst that is present, which is of redox in nature, and we know what is redox, right? It can continuously change its oxidation state depending on the partial pressure of the oxygen in the gas phase that is changing. Okay. And what happens is that the ethyl benzene comes, it reacts with the available oxygen from the oxide material and forms styrene. Now, just because it's consumed those oxygen species from the lattice of the material, and the second cycle what we are doing, we are passing air which has some 21% oxygen, such that the catalyst is reoxidized, and then we have oxygen lean air at the outlet, and this cycle just goes on. And the material we are looking at is a core shell type of material, where we have calcium and magnesium oxide present at the catalyst core, and we have potassium promoted iron oxide is present in the shell. Okay. And from the in situ XRD, we are seeing under different conditions, oxidative environment, reaction environment, and over reduction environment, how things are changing or what are the oxide phases that is evolving during the reaction. Okay. So, what we are seeing is that when we are at the oxidation regime, this material here which is related to the calcium oxide and magnesium oxide are not present, and we have a new phase present which is a solid solution between potassium manganese oxide. Okay. But as soon as we are taking it to the operating regime, we are seeing that this calcium magnesium oxides are losing oxygens, because here what we are doing is that we are continuously flowing ethyl benzene, and that is continuously taking up oxygen from the oxide material. And as it is taking oxygen from the oxide material, of course, the material structure is changing, and that is being reflected as the shift in the XRD position. As you can see, there is a little bit shift towards the lower 2 theta degree that is happening during the reaction, and we are at a phase where we are seeing the over reduction. And why I am seeing over reduction? Because at this case we are now we are actually seeing these over reduced materials and all, and then when we reoxidize again, this phase has oxygen back, and then we can see all these things. So, for the core shell catalyst, this is just a schematic. It does not just stay at the same structure during the reaction, but it actually changes because of, well, actually not because of heating and cooling here, it is because of reduction and reoxidation. Okay. Okay. And with that, let us just look at some of the limitations by XRD. It is a bulk characterization technique. Our catalysis happens at the surface, but that does not mean that some of the bulk information are not going to be useful. That is why the last two examples I showed, where the oxygen, which is the reactive species for the reaction, comes from the bulk, we need to know how these transitions are happening, and until what extent we can reduce such that the catalyst can be reoxidized without significantly losing its prior activity. Okay. Too much of reduction, the reoxidation might not restore the original activity. Okay. And then peak deconvolution is difficult in the case where there are multiple oxide phases present and things are overlapped. Okay. Shearer equation, this gives us an average particle size and not the size distribution, and since catalyst, some of the reactions are going to be structure sensitive, where smaller particle might have a different pathway for the product formation, and the bigger particle will have a separate path to a different product. So, if we do not know the particle size distribution properly, we are not able to extract all those the catalytic information. And of course, in XRD, it is usually seen that the large size crystals actually dominate the peak. So, whatever is smaller than that, they are not going to show up that significantly as compared to the larger size particle. And the biggest thing that Professor Banaras has been talking in his lectures as well, XRD cannot see anything below 3 or 4 nanometer. So, if we have smaller nanoparticles like sub-nanometric or a nanometer, 2 nanometer type of thing, then XRD cannot help us. But Raman as a technique is very, very sensitive to those crystalline materials. Okay. Yeah, I do not think we have to go over the things again, it is just the same thing. And then do you have any question at present? Okay. Yeah. Okay. So, after XRD, let us go to X-ray photoelectron spectroscopy. So, we will start with little bit of working principle. So, in this case what happens is that we have the sample which is irradiated with low energy X-rays, and typically this energy is below 1.5 kilo electron volt. And when this energy is irradiated on the sample, one of the core electron is knocked off from the sample electronic shell. Okay. We know the incident X-ray energy, we can calculate the velocity or the kinetic energy at which this core shell electron is ejected, and the difference is going to give us nothing but the binding energy of this material. And since the binding energy is the fingerprint of different material, from that we can say which material is under investigation. Okay. So, this is a typical outline of how XPS works. We have a low energy X-rays that is bombarded on the sample, the photoelectrons are emitted, and we have a hemispherical energy analyzer. So, we have a positive and a negative voltage here, and depending on the velocity, the electron will be bombarding on at different position of the detector, and based on that position we can back calculate the kinetic energy at which the electron is coming in. One with a higher energy will be bombarded here, one with a lower energy will be bombarded towards the left hand side. Okay. So, utilization, we can have elemental information, we can have chemical state information. This is sensitive to the surface region, some 1 to 3 nanometer. So, in true sense it is not a surface technique, because surface is just one atomic layer which is 0.3 or 0.4 nanometer, and what we are seeing is that some 1 to 3 nanometer from the surface, which is some 8 to 10 layers. So, it is not just the surface information we are getting little bit on the subsurface region as well. Okay. And it has a very sensitive detection limit, 0.1 to 1% of the material present can still be captured by XPS, and with some sort of calibration, it is quantitative in nature. So, we can see in that surface region within 8 to 10 layers what is the composition of different material that is present. Okay. There are few limitations, it cannot detect hydrogen or helium, it may damage some of the sensitive materials, and typically the XPS what we see in our institutes are operated in ultra high vacuum conditions. So, 10 to the minus 10 torr type of thing, but for our catalytic reaction we need higher temperature and the reactive gases to be flowing. Okay. For that, in recent days there is development on the NAP XPS, and we are going to take all the examples from the NAP XPS today. It is near atmospheric pressure X-ray photoelectron spectroscopy. It is called a near atmospheric pressure because the pressure is of course higher than the ultra high vacuum XPS experiments, because we are flowing some gases, but it is still not as close to the atmospheric pressure, it is slightly below that. So, it is in between that atmospheric pressure and ultra high vacuum conditions. So, we are trying to bridge the gap, but not there yet. Okay. Okay. Since we are talking about the X-ray photoelectron, so there are some analogous techniques to it which also give us the same type of information on the chemical nature of the material. So, let us just look at those things a little bit. So, the X-ray photoelectron of course is that the beam of X-ray comes and that kicks out one of the core electron from the inner shell, and the X-ray photoelectron is generated. But instead of that, if you have a UV photoelectron, so instead of X-rays we have UV lights, and just because the UV lights have lower energies than the X-rays, they will not be able to kick off the core electron, but the outer set electrons which are not strongly bound to the atom's nucleus, they can be ejected, and in this case it is called a UV photoelectron. Okay. And then what can happen is that uh, uh, when the X-ray photoelectron happens, so there is an hole here which is like an empty electron space, okay, and a higher level electron can come and fill this hole, and the difference in energy it can just emit, which is called the X-ray fluorescence, okay, or the higher electron can come here and whatever energy is generated, now that is kicking off one outer shell electron. So, that is called auxiliary electron, it is a secondary electron. Okay. So, these are some of the techniques. I just wanted to make sure that when the XPS happens, actually the fluorescence and the auxiliary electrons are not very much avoidable, but then the type of the detector and all these things we are dealing these days, they are selectively taking the photoelectron and trying to avoid these secondary emissions and all. So, some of the typical X-ray sources are magnesium or aluminum K alpha lines, and they are about 1.2 and 1.5 electron volt, kilo electron volt each. There is synchrotron X-ray sources, and just like the XRD, these are really powerful X-ray sources, and they have a tunable energy. Instead of X-ray coming from one single source tube where your copper or magnesium or aluminum is present, now you have a tunable energy, and we will see one example how that tunable energy can give us more surface sensitive information than the typical XPS we have present on a bench scale in our academic institutions, and this is typically done at ultra high vacuum conditions. So, some of the things on this diagram is that we have the X-rays generated, and there are X-ray monochromators which are radiated on the sample, and then the photoelectrons which are emitted from the sample, they go through the hemispherical energy analyzer, and just like I said before, you have a positive and negative potential that is applied, and depending on the velocity at which these photoelectrons are ejected, they will be put on these detector plates. Okay. But at the same time, what happens is that when we have the photoelectron emitted, we are leaving behind a positive charge because we are taking up an electron, right? And then we need to neutralize that charge, otherwise the subsequent photoelectron that is coming from the sample is going to give us erroneous data. Okay. And for that, we have electron flood gun, where very low energy electrons are flooded or bombarded to the sample just to neutralize those charges. Okay. Now, coming to the NAP XPS or the near atmospheric pressure. So, on the previous case, this is ultra high vacuum 10 to the power minus 10 torr, but in this case now we can operate at ultra high vacuum condition, but at the same time we also have provision for like incorporating little bit of gas to the analysis chamber or the sample chamber, okay, and we can go up to 1 torr, and in typical cases we can go up to 1000 degrees Celsius. So, there are two different types. So, for resistive heating, and the maximum we can achieve is about 600 to 650 degrees Celsius, but with laser heating we can go up to 1000 degrees Celsius. Okay. And this is one diagram for the NAP XPS where you can see, okay, so this is the chamber where the sample is kept, and this is enlarged here, and you can see the sample is here. You have the beam of X-rays that is coming in, and you have the gas valves, the gauges and everything that is taking out the gas, and this tip is really small, which is enlarged here. Okay. These are say a couple of hundreds of microns, so sub millimeter region. Okay. And only a very small part of the X-rays, so small part of the photoelectrons that goes, and then that is being continuously pumped the gases out, and then it goes to the hemispherical detector. And in many cases these NAP XPS at their outlet are always connected with an RGA, residual gas analyzer, or a mass spectrometer, such that if reaction is happening, we will be able to see the products that is also evolving from the catalyst surface. Okay. And here I am showing a typical diagram of in situ cell for the NAP XPS, where you can see the sample can be mounted, it can be heated to a higher temperature with some amount of gases being flown, that is shown in this diagram here. Okay. Few examples how XPS can be utilized to determine different things. So, the first example that we are going to see is on CO2 hydrogenation to methanol. And the catalyst that is we are looking at here is that it is a copper 111 surface, a copper 111 phase, and the surface has a little bit of copper oxide present on it. And then we have deposited about 0.2 monolayer of cerium oxide. So 0.2 monolayer means 20% of the total available sites on the surface of the copper oxide is being taken up by cerium oxide. Okay. And we are trying to see under different environmental conditions what are the most abundant surface species that is present on the sample under the conditions where we are running the NAP-XPS experiments. So we have the pristine samples and then we exposed it to 30 milliliter of carbon dioxide at 300 Kelvin, and what we are seeing here is that we have a peak that is corresponding to the adsorbed CO2 species, and after that we incorporated, in addition to this 30 milliliter of CO2, some 270 milliliter of hydrogen at the same temperature 300 Kelvin. So now we have CO2 to H2 ratio of 1:9, okay, and the total pressure is 300 milliliter at present, okay, and at 300 Kelvin which is close to the room temperature, we have mostly the CO2 species that is adsorbed on the surface and little bit on the format. But as we are increasing the temperature from 300 to 400 to 500, what we are seeing is that the peak that is coming from CO2 is going down and down, whereas the format peak is going up and up. So that shows that how the hydrogen is reacting with the adsorbed CO2 to form format at higher temperature. Now, this only gives us the information that what is there on the surface under such conditions. No guarantee that these are going to be the reaction intermediate, but yes, these are the most abundant surface intermediate under such conditions, okay. And this is the oxygen 1 spectrum we are seeing. We can look at the carbon 1s for the same thing and we are seeing the same part. So the CO2 peak intensity is going down with temperature, whereas that related to the carbon which is associated to the format species is going up and up, okay. Okay, so that gives us information about the surface adsorbed species. Now what else we can do is that we can do elemental analysis. So this is another example on CO2 hydrogenation to methanol, but here now we have a different catalyst. Instead of cerium being deposited on copper oxide, now we have copper on cerium oxide, and the cerium oxide we have has two different structures. One is a nanorod, another is a nanosphere, and fixed bed experiments, high pressure, high temperature methanol synthesis conditions shows that one of these is more active than the other, and we are trying to figure out from XPS what could be the possible reason for higher activity for one over the other, okay. And what we are seeing here is that the XPS spectra were collected at different conditions and different temperature. We have spectra at fully oxidized condition, we have spectra at reduced condition. Then after the reduction we have incorporated the gases, and then under such conditions what we are seeing with increasing temperature when we have both CO2 and H2 present for the top 3 spectra, okay. And what we are looking at in this case, we are looking at the cerium oxidation state +3 versus +4, or the relative distribution between the +3 and +4. Like I said, XPS can be quantitative in nature, okay. And we are comparing the nanorods to the nanospheres, and it is shown in this one. So on the x-axis we have the different conditions which are followed here. On the y-axis we have the concentration of cerium 3+, which is the reduced phase of cerium, okay. So when we have the fully oxidized sample here, what we are seeing is that a cerium 3+ concentration at surface or near the surface is almost 0, which is obvious for the reason is that because of the oxidation, all my cerium is most likely to be present in the 4+ oxidation state, correct. Now we are reducing it, and because of the reduction condition, we are seeing that about 25-27% of cerium 3+ is formed on the surface for both the samples. And then at room temperature, when we exposed this reduced material to hydrogen and CO2, because CO2 is a mild oxidant, CO2 slightly oxidizes some of the reduced cerium, okay, and hence the cerium 3 plus concentration has gone down. But now under the same gas flow, that is CO2 plus H2, now we are increasing the temperature. Now with increasing the temperature just because hydrogen is present, that's re-reducing the material which was partially oxidized by the mild oxidant CO2. And under such condition, what we are seeing is that for the nanospheres, the sample reduces more compared to the nanorods. And there was one possible explanation is that because the nanorods at higher temperature has a higher oxidation state, that means more amount of copper oxide that is cerium oxide that is present, it's helping in chemisorbing CO2, and that could be the reason why these nanorods are more active than the nanosphere for the methanol synthesis reaction. But then again, one technique is not going to be giving you the full answer. It has to be a combination of multiple techniques indicating in the same direction. Okay. Another methanol synthesis catalyst, we have in this case the very famous copper zinc oxide type of thing. Okay, so there is one debate that is going on. Everybody is clear that the copper is present in the metallic state, but well, yeah. Okay, so in this case, what we have is that we have the copper zinc oxide catalyst, and then the two debates. The debate on the active side is that the active side could be copper zinc alloy, or the active side could be the interface between metallic copper and zinc oxide. Okay, and to do that, what the authors did here is that they completely reduced the zinc oxide to zinc, and then they exposed it to the reaction environment, which is nothing but CO2 plus H2. Okay, and with time they are looking at what is the amount of the products formed, which is nothing but methanol in this case. And they said in the first 20 minutes there was a continuous increase, and then the product formation just becomes stable. And when they compared it to the zinc oxidation state, because remember we started with copper zinc alloy both in the metallic form. Okay, what we are seeing is that the metallic zinc it has a binding energy of 1021, whereas the zinc oxide it has a binding energy of 1021.65 or something. And what we are seeing is that corresponding to the increase in the formation of the methanol, the zinc binding energy is continuously increasing to a higher and higher value, showing that the zinc is continuously transferring to zinc oxide, and that's remaining constant for the rest of the period of which they have done the experiment. So that said, even if we are starting with zinc, we will end up forming the zinc oxide during the reaction, which is the stable phase during the reaction. Okay. Now this is very interesting. Okay, I was talking about this benchtop XPS, where the energy X-ray energy cannot be tuned, but then we have synchrotron XPS, where we can actually tune the X-ray energies. Okay, and here what we are seeing is a bulk zirconium vanadate species. Okay, Uran XRD, Uran XPS, the regular one, you will see a zirconium vanadate species, and you will assume that the bulk is going to be reflected on the surface. But is it that the case in real? So for that, this synchrotron experiment, what it did is that, of course, we have the energy that is corresponding to the aluminum as well as the magnesium, which is like 1.5 and 1.2 kilo electron volt. And what we are seeing is that we are seeing peak both from vanadium 3p and zirconium 4p, right? But now as we are decreasing the X-ray energy to 500, 400, 250 and 150 electron volt, that means the depth we are probing from the surface is continuously decreasing, and we are concentrating more and more on the surface part. Although we are still seeing the vanadium 3p peak, but the zirconium 4p peak intensity has gone down significantly. So that shows even if the bulk structure is zirconium vanadate, the surface is enriched in vanadium. Okay, and that's exactly what we are seeing with the model and the experiments with the excitation energy. And if we are looking at the concentration of vanadium upon vanadium plus zirconium, multiplied by 100 as we want to look at the percentage. So, the surface is purely vanadium, whereas as we are going to the deeper and deeper region, of course, there is now vanadium concentration has gone down because the rest has been taken up by zirconia. Okay. Okay, so that brings to the end of XPS, and few things that I have to point out is that it's a surface sensitive technique, but in true sense it's not a surface technique. Surface technique means it's just gonna look at only the surface. What Professor Banares was talking yesterday, low energy ion scattering. It's a true surface sensitive technique. Here we are seeing near surface region 1 to 3 nanometer, and with tunable X-ray source from the synchrotron, we can actually have a better surface sensitivity, just what we saw in the previous slide with an example. Compared to XPS, NAP XPS is more powerful and relevant to the catalysis research, as we saw some of the examples, and of course some of the utilization and the limitations that we already discussed. Okay. Okay. So, after XRD and XPS, let us look at the X-ray absorption spectroscopy or the XRS. Okay. So, in this case, we are not dealing with low energy X-rays anymore. Now, we are looking at high energy X-rays, which can actually penetrate the bulk of the sample. Okay. So, the sample is irradiated with a tunable high energy monochromatic X-rays, and we are looking at the things at the detector at the outside. So, there are two major techniques. One is called the GENS, which is X-ray absorption near a structure. One is XEPS, which is X-ray absorption finite structure, and we will just look at these things a little bit. So, simply speaking, we have energy that is tuned from a very low value to a very high value. These are monochromatic but tunable X-ray energy. So, up to a certain energy, the sample will absorb the energy, but it is not sufficient for the electrons to go off. But then after a certain point, which is the binding energy, if the X-ray energy higher than the binding energy, then of course we will have the photoelectron that is coming out, and then we have the GENS part at this point and the XEPS part at the higher energy samples. So, the GENS is going to give us information about the local geometry, electronic properties as well as oxidation state, and we will see some of these examples. And the XEPS part is going to give us information about the nearest neighbor, the bond length and the bond disorder to some extent. Okay. So, utility, it is a bulk characterization technique, but we can use it to get information on the supported metal oxide catalyst where things are present within a monolayer coverage on an high oxide surface area support, high surface area oxide support. Okay. This is applicable to both solid, liquid and gas. In situ technique is available. It can be run at gases flowing and at high temperature. Okay. The limitation, we need synchrotron X-ray source. Okay. Getting a beamline time is difficult, and of course, when you get a beamline time, it is not too long. So, this cannot be your primary technique, but then again, if you have prior information on your sample and all, and you can take a couple of your representative sample to the X-ray source, you can do a few experiments there to get more information or to validate your hypothesis. Benchtop X-rays, they are coming up, but they are like really far in application as compared to the synchrotron X-rays. What you can get in synchrotron in a second or within a minute, for a benchtop X-rays it is going to take 24 hours. So, it is that different. So, no kinetic information, and if your sample is changing, it is evolving over that long period of time, then there is no guarantee that you are getting the real information. Okay, so a little bit on the instrumentation and the measurement principle. So, what happens, we have the X-ray monochromator. So, we have the incident X-rays. Now, two things, we can either do it in a transmission mode or we can do it in a fluorescence mode. So, in the transmission mode, what we do is that we pass it through the sample. So, we get the transmitted beam, or we pass it through the reference sample such that we get the reference intensity and all. And what we are trying to calculate is nothing but the absorption coefficient, that is how much of the X-rays that is being absorbed by the sample when we tune the X-ray energy from a low energy to a higher energy. Okay. And for the transmission, we look at this formula to calculate the mu E, which is the absorption coefficient. For the fluorescence, it is slightly different because here after the absorption there will be some emissions, and your mu E is nothing but your IF upon I0. IF is the intensity of the fluorescent light, I0 is the intensity of your incident beam. Okay. So, let us just look at some of the examples. The first one being local geometry. Okay, so here I have tungsten oxide on silica. This is similar to the examples that we have been seeing with Professor Banaras' lecture, that is vanadium oxide on titanium, moly oxide on silica, on alumina on titania or zirconia. So this is, in this case we have tungsten oxide on silica, and we have 3 different samples with tungsten oxide loading 4 watt%, 8 watt% and 20 watt%. Okay, and we are trying to figure out what could be the possible geometry of tungsten oxide in all these cases. Okay, and for that we have the Jain spectra that is collected for all these samples. Well, I mean, the samples are here, but these are the reference materials. Let's just look at one very crucial feature here, is that we have taken 3 different reference material. We have the cerium tungstate. Now, as I mentioned a minute back, we have tungsten oxide present here in tetrahedral geometry and in isolated form. Okay, we have WO3, in which the tungsten is present in octahedral form like WO6 structure, and a 3-dimensional polymeric chain. Okay, now what we are seeing is that the difference in the pre-edge peak. Okay, for one which is in the tetrahedral unit, there is a strong pre-edge peak that you can see in this purple curve, but on the red one, where there is no tetrahedral geometry, only octahedral geometry, I mean, depending on the purity of this reference material, that pre-edge peak has significantly gone down, correct? Now, from little bit of this background of chemistry, on the octahedral, which has a center of symmetry, the transition from the 2s to T2 electronic transition is forbidden, whereas for the tetrahedral geometry, which does not have a center of symmetry, this transition is allowed. Okay, so let's just use that information to see what is the possible local geometry of tungsten oxide in these 3 samples with varying tungsten loading. For the 4 watt% tungsten, we see a strong peak at the pre-edge, and as we are increasing the loading, the strength of the peak is going down and down. That means with increasing loading, what we are seeing is that for a low loading, where we were below the monolayer coverage, by the way, the monolayer coverage for the tungsten oxide on silica is about 6 watt%. So 4 watt% is definitely below monolayer coverage, and we have all the tungsten oxide present on the surface as isolated WO4 species, maybe slightly distorted tetrahedral structure. Okay, but as we are increasing the loading to 8 and 20 watt%, of course, now we are going way beyond the monolayer coverage, which is about 6 watt%. So we are forming WO3 crystals. Now, once we are forming those crystals, we are seeing that this pre-edge peak intensity has gone down. And of course, if I can do a simple linear extrapolation kind of thing or interpolation kind of thing for a pure substance with a WO4 structure versus a substance where there is 100% WO6, what is the area under such peak, and based on that, what I found from my sample, I can actually back calculate the percentage of WO4 in tetrahedral state versus the percentage of WO6 in octahedral configuration, and that is what that has been shown here. For the 4 watt% sample, I have 92% of WO4 species present. For the 20 watt% sample, now the percentage of WO4 is really low, which is 40, or the rest 60 is corresponding to the octahedral state. Okay, apart from the local geometry, we can also have information on the oxidation state, and here we have several samples. So one sample is tungsten oxide deposited on a carbon support. In another case, we have tungsten oxide deposited on carbon support, but now we have added platinum as a promoter or another material to the catalyst, correct? So what we are seeing is that again the Jain spectra for the tungsten L1 is, and we have the WO3 here, which is the dotted dark black curve. Okay, and similar to the previous one, if we follow this dotted bar curve, we do not see a significant pre-edge peak. That's because WO3 is octahedral in structure and it has a center of symmetry. Okay, but if we look at the tungsten oxide that is deposited on carbon, let's forget about this 1R. 1R means this is atomic layer deposition, that's one cycle. So WOX on carbon, which is the gray dotted line, we can see there is a pre-edge peak now appearing. Okay, that means that gives us some information. This tungsten oxide on carbon is present in it has a significant portion of tetrahedral WOX unit or WO4 unit. But now let us see what happens when we add the platinum. When we add the platinum, you can see, which is the dark blue solid line, as compared to the dotted gray line, we have the pre-edge peak even more significant. Okay, so that gives us information this platinum addition is helping in getting us more WO4 units, which was less when the platinum was not present. But now when we take the same catalyst, but now we reduce it, of course the structure is changed because oxygen has been taken up, that pre-edge peak has completely gone. Okay. There is one key point to see here. Now look at the dark blue line here and the light blue line here, okay, and look at the position from which the edge is starting. So the dark blue, it starts at a slightly higher energy, whereas the light blue, it starts at slightly lower energy. So depending on at the rising edge, we can have the information about the oxidation state of the material, and that's something that we are going to see in the next example. Here we have moly oxide species on ZSM5 support, okay, and we have different conditions and different gen spectra for these moly oxide species present. Okay. So in the first case, we take the MOO3 and we take the moly on GSM5. By the way, this is 2% moly, so which is a very low loading where the full dispersion is expected to happen. It's below monolayer coverage. Okay, and what we are seeing as compared to the MOO3, which is not exactly the tetrahedral structure, the moly oxide on GSM5 has strong tetrahedral characteristic. As you can see, the pre-edge for the solid lead line is significant as compared to the dotted red line. Okay, but now we are taking that catalyst and that moly on GSM5 and we are doing a treatment. So that moly on GSM5 in air has a strong pre-edge peak, and when we are exposing it to a condition 20% methane and helium, because this catalyst is used for methane dehydroaromatization. So methane comes, reacts on the catalyst and forms benzene, toluene or xylene, and such conditions the oxygen from the catalyst is taken up, some carbon is left behind, and we will see that some oxycarbonic type of structure is formed. And when the catalyst is reduced, just as we saw in the previous example, here the pre-edge peak is gone. Now we are seeing that for the solid black line, which is moly GSM5 exposed to a reducing environment of 20% methane in helium, we have that pre-edge completely gone. Okay, so that reduces the sample, but now we compared it to the moly carbide, which has a lower oxidation state of moly, right, +2, and we see similar kind of things. But now instead of just 20% methane on helium, we add a little bit amount of CO2, just 1%. It's a mild oxidant and we are adding at a very low concentration, and still as compared to the black, what we are seeing is that we have now that pre-edge peak appearing a little bit as compared to the black one, but that little bit is because it's 1%, and of course not 1% oxygen, which is strong oxidizing agent, it's 1% CO2, which is a mild oxidizing agent. And what we are seeing more is that look at that pre-edge peak, the rising edge, the energy at which that is happening, the red being fully oxidized, it happens at a higher energy as compared to the black, which is a more reduced form, which is happening at a lower energy, and the blue one, which is intermediate, because we have a little bit of oxidant added to it along with the reducing agent. And that's what has been shown on this plot here, where we are like zooming into this step, and then we are actually looking at the point at which the energy is rising, and then we have the reference material here, which are nothing but these solid circles. So we have different moly oxide materials, moly +1, +2 and all these things, and depending on the oxidation state, we are seeing that the energy at which the rising edge will appear is increasing and increasing. And as we are putting on the same plot, our samples are treated in different conditions. For example, in this case, of course, the moly on GSM5, it's completely oxidized, and hence the the energy at which the rising edge is happening is at a much higher energy as compared to the last one, which is the black curve here, where moly is exposed to a reducing environment of 20% methane. Okay. So that's on the gens part. Let's look at the accepts part, because so far we have been looking at that rising edge, pre-edge type of thing to look at the local geometry and oxidation state. Now let's look at the other part, which is X-ray absorption finite structure, and it is for the same catalyst, that tungsten oxide on silica. We have the 4%, 8% and 20% tungsten deposited, and what we are looking at is some of those same reference materials, and based on that how the peak is appearing. Okay, so if we have some information on the structure of this catalyst, so this is like a model fitting, and we can take that model like we have a mixture of tetrahedral and octahedral, or we have just pure tetrahedral or pure octahedral, and then we keep the parameters free on the bond length as well as the number of nearest rubbers that the tungsten can have, and we try to fit the experimental data as closely as possible from our model, and based on that the best fit gives us the tungsten oxygen bond length. But then again it always depends on the type of the model that you have chosen at the beginning. If that is pretty close to the type of the sites that is present in your catalyst, you will have a much better fit as compared to the one where you are far away from the practicality. This is the same moly on GSM5 for the methane dehydroaromatization, but now we are looking at the accepts part of that thing for the freshly calcined catalyst, which is fully oxidized moly phases present and after the reaction, and we have the bulk moly carbide species present, where we have the moly species and the moly carbon species, but for our sample we have moly oxygen present, and we have moly oxygen silicon present, but we do not see any moly coordination or moly oxygen moly coordination. So if we are not seeing any molybdenum oxygen molybdenum, that means there is no polymerization. These are isolated moly sites. During the reaction, what we are seeing as compared to the moly oxide, we have moly oxygen bond that is present, yes, but we have additional bond of moly carbon as well, and we have moly oxygens are all moly bonds are also present. Okay, so it's not, so the fully oxidized catalyst is moly oxide, the moly carbide where there is no oxygen, but during the reaction what we are seeing is that we have moly oxygen, moly carbon as well as moly just because the moly oxygen is present. So the catalyst after exposure to the reaction conditions, it's not fully oxidized, that is MOOX, or it's not fully carbide, that is MO2C, but it's somewhere in between, which is an oxycarbidic phase type of thing. Okay. Okay, so that brings to the end of the X-ray absorption spectroscopy. So the thing is that we will always get bulk information because it penetrates through the material and it gives you the average information over all the sites. So molecular level information is lost, that is number one. But then from the gens part with fitting and all, you can extract little bit of how much of this phase present versus the other phase present, but that's it. But it can be applied as a surface technique to some of the examples that we saw, like low percentage of tungsten oxide on silica or low percentage of moly on ZSM5, where you have submolar layer coverage and it's sensitive to those things. Just like Raman, even if it penetrates to the bulk, we are able to get the surface information because at the relevant Raman vibrations, the vibration from the support does not appear in that regime. Okay. In situ analysis is possible, but the major demerit is that we need a synchrotron source. Okay. The gens can give us information about the electronic structure, local coordination and geometry and oxidation state, whereas the accepts, as we saw, can give us information about the nearest neighbor as well as the bond length. Okay.